So here we have the next theorem. On the base of the vector space V have the same size. So if both set 1 contain n vectors v1 to vn and set 2 contain m vector u1 to um, and both these sets are base for a vector space V, then m must be equal to n. So they must have the same size. So if they are two base of a vector space V, they must have the same size. And we use the previous theorem. So proof. So recall the previous theorem say that if this is a basic of the vector space V and this is m vector, the set of m vector in the vector space V, and they are linearly independent, then m less than equal to n, right? Because if m bigger than n, strictly bigger than n, then this set must be linearly dependent, right? So maybe I recall the theorem. Maybe I just copy the theorem. Here's the theorem. Say that if v1 to vn is a basic for a vector space V, then any collection of m vectors in V where m is greater than n is linearly dependent. So you have a set of where there's more, the number of vectors is more than the number of vectors in the basics, then it must be linearly dependent. So recall this theorem. Okay, and here is our main proof. So by say theorem A, we know that since v1 to vn is a basics of V, okay, and u1 to um is linearly independent. Okay, so let me say like one step before that this set is a basic of the vector space V. In particular, they are linearly independent, right? Because two conditions for the basics is linearly independent and span the whole vector space, right? So we use this condition. They are linearly independent. And because they are linearly independent and this one is the basics, this means that by this theorem A, m is less than or equal to n. Alright, maybe here's a comment. Otherwise, this means that m strictly bigger than n, then this set u1 to um is linearly dependent by theorem A, right? Which not true, because by hypothesis this set is a basics of the vector space V. In particular, this set is linearly independent. Okay. Now similarly, by theorem A, we have, so by theorem A and by the following reason, u1 to um is a basics of V and v1 to vn is linear independent, then we have n must be less than or equal to m, right? So now we have two conditions. The first one is m is less than or equal to n. The second one is n is less than or equal to m. Therefore, m must be equal to n. This proves that two bases of a vector space or any basis of a vector space must contain exactly n vectors. So, which prove the theorem. All bases of the vector space V have the same size.